Hello and welcome back to Columbia Physics Preceptor TV. Today we're going to do Lab 1.3, Velocity Acceleration in G. Before we go ahead and talk about the actual lab, let me talk a little bit about the equipment we'll be using. Let me draw a picture of it first, so you can really see what's going on. Let's see. You have an air track here that spurts out a bunch of air, and this glides back and forth on it, and by having all that air in there, you eliminate a lot of friction. So this is the air track. This thing here is a sonic ranger. And it sends out a bunch of impulses that bounces off this cart and back to the sonic ranger, and it measures the position of this thing at every point in time. And it's hooked up to a computer. So this thing, first of all, has a couple of settings. It has one that's very narrow, which you're going to be using with the air track when this thing goes back and forth. It has a very narrow beam. And another one where it's a little wider, which you're going to use in the first part just to get accustomed to this stuff, which you can use when people are walking and you measure larger things. The computer has a specific computer program, which is pretty straightforward. It has like a start and a stop button that you can start and stop data taking from the sonic ranger. And it'll actually graph two graphs. It'll graph the x versus t, the position versus a time. And it'll also graph the velocity versus a time. So you'll get two different graphs when you start data taking here. That's pretty much all you need to know about the equipment. The actual labs are, the first part is just for you to get used to it. You're going to use this setup, and you're going to take the sonic ranger, and instead of hooking it up to this, or instead of pointing it towards the air track, you're going to point it at one of your lab mates. And you're going to have that person walk back and forth at a constant velocity. You're going to try to make it as constant as possible. And you're going to look at these graphs afterwards to see how good you actually were at walking at a constant speed. That's part one. It's just to get used to the equipment. The actual lab kind of starts at part two. It's a coefficient of restitution. This time you're going to have this cart move back and forth, and you're going to have it bounce off one of the ends. So it's going to come in with some initial speed vi, and after it bounces over here, it's going to come out with some final speed vf. Now, if everything was perfect, and kinetic energy was conserved from here to here, the initial and the final speed should be exactly equal to each other. Of course, when you bounce into this end here, you lose some energy to, elastic energy, friction, and all that stuff at the end. So V final is actually going to be slightly less than V initial. And a way to quantify this is with this coefficient of restitution, which is defined as E is the final speed divided by the initial speed. And you take this absolute value to make sure that you get a positive number, because if VI is positive, then VF would be negative. But you shouldn't worry about that. It's just the value of VF divided by value of VI. So again, if everything was ideally, this should be equal to 1. Of course, you're going to get something smaller than 1. You're going to do this in two ways. You're going to do it like the measurement only once, but you're going to look at the two different graphs that the computer produces to get two different values for this. The first one is by looking at the x versus t graph. By taking, 5 of the x versus t before and 5 of the x versus t after you do this, before and after it goes through this collision, you can draw a best fit line for these 5 points and figure out what the speed is before and after. And by doing that, you'll get a value for the coefficient of restitution. The second way to do this is to just look straight at so this is x versus t, you look straight at the v versus t graph, and you take 5 points before and 5 points afterwards, and you just average them. Average the ones before and the average the ones after. So you'll get another way of finding VF and VI, and hence another way of finding the coefficient of restitution. That's the second part of the experiment. The third and final part of the experiment is in regards to gravitational acceleration. Gravitational acceleration, g, since it's about 9.8 meters per second squared, it can be kind of difficult to measure it directly because things accelerate pretty quickly. So we're going to use our air track in this case and just raise it up a little bit. using metallic shims that are provided. And I think they are, let's see, 1.24 millimeters thick each. So you might need to use a bunch of them to raise it up a sufficient amount. So now this entire thing is on some incline. And this rider on top experiences a gravitational acceleration g down, but because it's only an incline of some angle theta, the actual acceleration, ax, that is you'll actually be able to measure, is just g sine theta, so it's much smaller. And it's by measuring this this acceleration, and also this angle, or sine of the angle, that you can find the gravitational acceleration. And again, you're going to do this in two ways. But one way is by looking at the x versus t graph, and the other one is by looking at the v versus t graph. So, if you recall that x is equal to x naught plus v naught x t plus 1/2 ax t squared, by taking 5 of the data points while this is accelerating like this, and measuring what x naught is, v naught x is, and measuring what the time difference between the point you're interested in and your original point, you'll be able to determine what the acceleration is. You'll get 4 values, because if you have 5 points, you have 4 intervals. So you get 4 values for A. And then you're going to average these 4 values to get some good quantified number for what AX is. That's the first way of doing it. The second way of doing it is going to another equation saying that the speed is equal to initial speed plus the acceleration times time. And now by taking v and graphing it versus t, you'll get some straight line, and the slope of that straight line will lead you to some understanding of what this acceleration is. So I think you're supposed to do, just take a few points and figure out what the slope is. So 2 ways of finding the acceleration. Then once you have the acceleration, since you optimally want to find g, you need to figure out what sine theta is. But since you know how many shims you put under the air track, and you know that it's 1 meter long, sine of theta is just this height h divided by 1 meter. So once you know sine theta, instead of measuring the actual angle theta, you only need sine theta. By knowing sine theta and the acceleration, you can find g. And that's pretty much it. So good luck with your experiment.